As I mentioned earlier, energy is a raw material with data that increasingly and making the energy system more efficient. So let's spend some time talking about each of these themes. Let's start with AI. As you know that we are now, it is very clear that AI revolution is here to stay and is accelerating significantly. We started up with perception AI, moving to generative AI, the ChatGPT moment in 2019, and more AI is turning agentic, meaning it can go autonomously take actions on your behalf with set conditions. And the next wave we believe is physical AI. So that is the ability to perceive physical environments, understand them, interpret them, and take actions on all of that. So what does all of this mean? It means that the demand for intelligence and compute is going to go up significantly, even more so than what we see today. There are also three scaling laws that are at play. So we've got pre-training, post-training, and test time scaling. So you guys, probably experience DeepSeek and thinking models. These days you got reasoning models. What used to be a straight shot answer just a few years ago, you put in ChatGPT a question, it would regurgitate an answer from memorization. Now the models are getting smarter. They look up data from the internet. They look up internal databases. So meaning the amount of compute that is needed to get to a very high level of accuracy will continue to grow up. All these three scaling laws are driving up the amount of compute needed for AI to be more sort of efficient and valuable. So then how do we meet all of this demand? AI factories. Like we have physical factories that take raw materials and power and generate goods and products, we have AI factories. These AI factories take electrons or electricity as input and then data as a raw material. The output is intelligence. So that intelligence is applied everywhere and is ubiquitous, and these tokens are valuable, like we just saw in the video, in every aspect of human life. Energy growth is driven by these AI factories going everywhere, in addition to other value drivers that we have seen. So as we also know, we don't have infinite amount of space in AI factories. So we need to try to drive significant of compute for the same sort of space that we have. So one of the measures that NVIDIA looks at is tokens per watt, per dollar. So we want to try to bring down the amount of cost that it takes to generate tokens, bring down the amount of energy consumed while increasing the number of tokens. And that's why we are on an annual cadence of hardware, and we go through significant amount of refresh cycles and R&D efforts to make sure that the compute that we're putting out there is as energy efficient, as dollar efficient as possible. But needless to say, however, the amount of energy density each of those racks have is continuing to go up, right? So with some of our partners, we're starting to look at 800 volt DC, as in the amount of energy that goes into a rack is going to be 800 volts moving forward. So that means more dense compute, more power per rack, and more tokens per rack that tries to bring down the cost of tokens and increase the efficiency at which we are generating AI. We are also, I think, innovating heavily on the inference side. You see a chart here where from Kepler all the way to Blackwell Ultra, the amount of energy required to generate tokens have been orders of magnitude reduced. That can be done only through extreme co-engineering. So we work with, from the chip all the way to grid, all the partners involved in that ecosystem. We try to bring together in a single system and optimize it at every layer of the stack. Unlike traditional data centers, AI is a systems problem, meaning data centers run a large number of very small workloads, whereas AI runs large number of small workloads. So that way you can then optimize, at every layer of the stack, from chip to the rack to cooling to power, inside the data center and then outside. And we are championing a strategy called chip to grid and grid to chip, which we're going to get into that a little bit here. So what are we doing to drive up this kind of efficiency? We use our own technology called Omniverse to try to simulate before we build. Let's watch a quick demonstration video of how we are applying this technology for extreme co-engineering so that we can get those types of numbers that you've seen.
The world is racing to build state-of-the-art, large-scale AI factories. Bringing up an AI gigafactory is an extraordinary feat of engineering, requiring tens of thousands of workers from suppliers, architects, contractors, and engineers to build, ship, and assemble nearly 5 billion components and over 200,000 miles of fiber, nearly the distance from the Earth to the Moon. The NVIDIA Omniverse blueprint for AI factory digital twins enables us to design and optimize these AI factories long before physical construction starts. Here, NVIDIA engineers use the blueprint to plan a 1 gigawatt AI factory, integrating 3D and layout data of the latest NVIDIA DGX SuperPods and advanced power and cooling systems from Vertiv and Schneider Electric, and optimized topology from NVIDIA Air, a framework for simulating network logic, layout, and protocols. This work is traditionally done in silos. The Omniverse blueprint lets our engineering teams work in parallel and collaboratively, letting us explore various configurations to maximizing TCO and power usage effectiveness. NVIDIA uses Cadence Reality Digital Twin, accelerated by CUDA and Omniverse libraries, to simulate air and liquid cooling systems. And Schneider Electric with ETAP, an application to simulate power block efficiency and reliability. Real-time simulation lets us iterate and run large-scale what-if scenarios in seconds versus hours. We use the digital twin to communicate instructions to the large body of teams and suppliers, reducing execution errors and accelerating time to bring up. And when planning for retrofits or upgrades, we can easily test and simulate cost and downtime, ensuring a future-proof AI factory.
So there you've seen how we're applying simulation and AI technologies to build AI factories themselves, all the way from design to build to operate, not just with NVIDIA, but all the partners that provide into that ecosystem, all the way from racks to liquid cooling, to mechanical, electrical, plumbing, to control systems. All of those things, we consider that as a single unit. And we design all of that inside Omniverse. And we try to then simulate multiple hundreds of scenarios based on the workloads that are expected to run in that AI factory, so that we can get the most amount of power, most amount of efficiency for a watt of power that costs the least amount of money. So that's applying AI and simulation to build AI factories. Now, yeah.
That's like for the actual physical construction, or when the workload actually runs on the setup?
Before we do anything at all, before you put any shovel in the ground, the first thing we do is we take the layout of the factory, we try to understand what workloads are running there, and we simulate the entire design, build, and operate value chain across the board before we actually do anything. So design, build, operate, everything is built inside Omniverse, and then we go to the actual process of doing it, right? Simulate before you build.
So for example, you have shown that heat and other flow. So effectively the entire CFD simulation has already been done.
CFD, yes,
Okay.
yes, yes. That's how then you can know how to optimize the system that you're working in. Yeah. So I think the same technology is now starting to come to the energy sector. We've got lots of long-standing challenges in the utilities industry. As you know, the current form of grid is 100 years old, the Tesla Edison grid, with generation, transmission, and distribution being siloed. A lot of times there is not a lot of visibility in real time on how demand and supply equations are changing. So because of that, you will have to run suboptimally the grid, and that prevents a lot of good efficiency to be put on the grid. So we're trying to then get the same kind of capabilities to work on the grid. Let's just talk a little bit more about how AI is coming to help the energy industry. So in the energy industry, I think we've got many challenges that we're trying to currently solve for. As more and more renewables are getting integrated into the grid, we know that renewables are very intermittent. So one of the challenges that we have is to predict the amount of energy that's needed, especially with renewables integrated to the grid. Predictive maintenance and asset inspection is a big thing because biggest cost and value comes by managing maintenance properly inside your utility system. Load and demand forecasting is another challenge, right? So you're always trying to figure out how much load is going to come on the grid and also predict and forecast how much power is needed so that you can then balance the generation and the consumption side of it. A real-time grid optimization is key. You want to try to make sure that you do a lot of these things in real time so that you can react instantaneously to changing demand conditions. Cybersecurity and OT enhancements, as you know, grid is considered a critical infrastructure. A lot of threat actors, target the grids of countries, as we've seen in a lot of political and geopolitical conflicts. So protecting the grid using AI is also a big sort of use case. Overall, I think the goal is to really lower the cost, maximize the renewable integration, the power sources that are put on the grid, and then improve reliability and resiliency of the grid. I think physical AI is also coming to a grid. We've seen autonomous cars. If you have been in one of them, you would be amazed by what you see. Lots of robots being put in factories, as you know. Humanoid robots, you saw some examples of humanoid robots taking off. Surgical robots are here from Intuitive Surgical and others that do precision surgery. Now, the same kind of capabilities will start coming to the grid, right? As you know, the electrical grid is the world's largest machine. There is no bigger machine than the electrical grid, right? And we believe it's a physical AI capability. It's ripe for that to come to the grid. The future of a grid is going to be a robot, and that robot will have a lot of edge compute capabilities that tries to gather intelligence on what's happening on the demand side of the equation and ships it up for the supply side to optimize it end to end. Physical AI, we look at physical AI as a 3-computer problem. A training computer to train the AI models, a simulation computer like the one that you just saw with the digital twin to simulate environments upon which AI has to run, and an inference computer, a computer that has to infer in the real time to apply AI or put it in action, right? So now let's spend some time going through each one of them. What are we doing in the training space? What are we doing in the simulation space? And what are we doing in the inference space? In the training space, there are lots and lots of data points that are available on the training side, right? So you have IoT data coming from lots of sensors in the field. You have camera and drone imagery of critical assets out there. You have historical load patterns that could be analyzed. You have weather data, which impacts significantly the usage of power in the grid. You have maintenance data, you have EV charging data, and you have grid operational data. All these data elements can be put together in building foundation models that could then be applied for various aspects of the energy grid management. The key thing here to note is that these models need to be very domain specific. A general purpose LLM is not going to fit the bill because electrical grid is a unique kind of system. It's got unique kind of constraints and opportunities. So domain specific models are what is key here to solve this problem. We have partnered with EPRI, Energy Power Research Institute. This is a global body that is sort of non-profit type of organization which collects data, manages the data about all these facets to create an open AI power consortium. So here we are bringing together a lot of domain specific data about power electronics and power system, and then helping companies to build domain specific models for various aspects of the grid. And then finally opening it up for developers to build apps and solutions that can be brought together in a way that it's an ecosystem that allows for innovation in this space. So who are the key players in this? In terms of core collaborators, the utilities, who are sort of the end users of all this technology. The national labs and academia have got a great interest in it because they are always looking at new ways of solving problems and new opportunities. The technology partners, like we partnered with NVIDIA, Microsoft, AWS, and many other partners because the energy challenge is a common challenge for the society and also for everybody, right? And then the three key pillars that we're using is to collect and develop data and AI models, which is the most important thing. Provide compute and sandbox capabilities for interested developers to be able to build and customize those models, and implementation and lessons learned, which is to share the knowledge and information on how things are going so that we can build cross-sharing and cross-learning of capabilities. All of this put together is the Open Power AI Consortium, with NVIDIA being one of the founding members of it, along with EPRI and others, creating a robust ecosystem of developers, data, AI models, startups that all want to solve the challenge of more efficient grid. Also, after these models are built, you want to try to build agents on top of it so that these agents can go do work in the real world. Interconnection studies is a big challenge, as you know. Whenever a source of energy is available to you, to put it on the grid, you have to run significant amount of interconnect what-if analysis study. And in the US currently, it is 2 to 3 years to put a new source of energy on the grid. It takes approximately 3 years for that to come online, which is significant amount of time. So we are partnering with our ecosystem partners to help build agents that can accelerate the interconnect study. Rate case analysis is another agent, right? So rate case analysis is a common problem in the digital grid solutions. So we're creating agents for that, helping with that as well. Fault detection and restoration agent. So agents that go look for faults proactively and try to provide solutions for it. Field operations, it's very important, a field technician going out, inspecting a piece of equipment, applying AI there to figure out that they can learn from the past experiences and fix those problems faster. Smarter dispatch and routing. Anytime there is an outage, on an average, apparently it takes around 9 hours or so to even detect where the outage is, especially in the severe weather events like a tornado or a hurricane, things like that. So we're working on trying to make that more efficient with this. Asset optimization agent. So how do you run your asset optimally, right? So it's a optimization problem with constraints, and you want to solve it, and AI can solve those things for you. Predictive maintenance. All of us who have worked in the heavy assets know predictive maintenance can save significant amount of money. And regulatory compliance and reporting is a big thing in critical infrastructure. It takes a lot of time from engineers and scientists and mathematicians and folks like that to do regulatory reporting. So anything that you can offload work from that to an AI agent could help them spend more time on high value work. So now that we've talked about, yes. Yeah. Yeah, so we've got a platform called Earth2, which simulates, a climate and earth and weather models. So we make those open source and available. There are lots of ISVs and customers that take that information and build climate and weather models that could be used by utilities as one of the data points to plan for demand as well as disruption and how to handle that, right? Yes. Yes, absolutely. So even wildfires as well, wildfire simulations, weather prediction, knowing which way the wind is blowing, all those types of things are also important. And we've got Earth2 platform and then simulations that make it, much more manageable than before. Yeah, I think those are the types of things, because it has to be married up with ArcGIS data. So what we do is we create an ecosystem. Our goal is to create an ecosystem, and the companies that actually are closer to the problem go solve those problems using our foundation technologies, right? Now that we spoke about the training, let's spend some time talking about simulation. We've partnered heavily with Siemens Energy to try to help them create digital twins of their assets, meaning individual components of the energy system, digital twin of the entire system and digital twin of the entire grid. So in the future, you want to have a digital twin of an entire grid that allows you to run lots of what if scenarios, analyze situations in real time, and then try to apply AI to it, because you got a digital twin which is going to be physically accurate, driven by laws of physics. You can confidently put more capacity on the grid, with simulations, with digital twins. So I think this is sort of the overall vision that we're driving with them, starting with the asset twin from a bushing, twin of a bushing, to a system twin that is a substation, to a grid twin that's an entire grid, and then to try to get to a totally autonomous in a digital grid is the end vision that we're after. Just some examples of the work that we've done with the bushing and transformer here. So we are also collaborating with SoCal Edison and Think Labs. As I mentioned, the interconnect studies are quite a challenging situation currently. And AI-based power flow simulation allows you to run thousands and thousands upon cases in short amount of period, that allows you to figure out what the challenges are and try to get those interconnect studies and results up and running faster. So using this, what used to take weeks and months, we're able to execute them in the matter of hours and days. Now let's just get to the last part of this entire story, which is the inference part. Yes. Yeah. Yeah. So oil and gas, I think we've got seismic processing with HPC, right? Lots of big customers like Exxon, Chevron, all these guys run on NVIDIA's HPC system for seismic processing. On the surface operations, we provide digital twin capabilities. We partner with companies like Aviva, Kongsberg. All these companies are starting to now use Omniverse as a technology to create digital twins. The moment you do it, you'll have a photorealistic representation of your complex refinery or a chemical plant. Once it's photorealistic, then you can actually do engineering maintenance inside a twin before you touch a wrench or a knob, right? Then people like companies like Chevron are also looking to use drones, robotics, those types of things to do maintenance. And the simulation computer is where a robot can learn how to walk inside a factory, how to do some work. And you do a lot of that training inside the simulation environment in the digital twin, and you apply this AI for inference at the edge. So for oil and gas, high performance computing for subsurface, digital twin for operations, Gen AI, agentic AI for co-pilots, knowledge management, those types of things. So lots and lots of opportunities, vision AI, at the edge. So we can talk about all those things as well after the session as well. Yeah.
So we spoke about digital twins for larger assets.
Yeah.
Let's say we want to create smaller distribution level.
Yeah.
Let's say a 200, 500 kilowatt distribution transformer
Yeah.
has to be converted into a digital twin.
Yeah.
Where smaller houses are being distributed power, or smaller industrial areas are being. So are there smaller edge devices that is NVIDIA working on something similar?
So let's get into that in a little bit, right? But we look at the grid as sum of parts. The smallest of the smallest component and the largest of the largest component need to all work together for this intelligent system to be autonomous, right? So that means every aspect of your digital grid has to be, inside a digital twin. It has to be intelligent. It has to, figure out what's happening in real time and autonomously able to take decisions to optimize the system end to end. So once we get into the inference side, let's see if that answers your question a little bit more.
Just one question.
Yes.
Regarding the training AI models, so in the same way we have multiple data sets, as you mentioned about the oil and gas industry.
Yeah.
So the simulation data and everything. So is there a specific type of model such as physical models that are specifically fine-tuned, or the general models are also, we can leverage those?
So what normally people do is they take one of the existing models and then they fine tune it with the data that is relevant to your use case. That's
Physical model or a general model?
A model is a model, right? So a model is a digital representation of something physical, right? Now,
Physical models are the models, newly generated models, which are the for specific use cases reference to these only.
so when we say physical AI, we are talking about a set of models that understands what's happening in the physical world. It doesn't mean it has to be a physical model. It is still a model that's understanding what's happening in the physical world, and then it tries to understand it and then try to come up with a next step, and that next step could be done by a robot or a manipulator or any kind of device, right? So if you take an example of a car, which is a great physical AI example, the car, the sensors on the car, autonomous vehicle is seeing what's happening out there. Then it is reasoning to figure out what exactly is happening. Then it is coming up with a set of actions. Those actions are then given to the vehicle to go to the transmission system, all parts of the vehicle to go take that action, whether I need to make a left or a right, right? Right. So the whole objective here is to understand the physical world and the laws of physics, and then try to have intelligence enough to know what action to take as a next step, right? So once we get into the inference, maybe, yeah, yeah.
You said the Omniverse you used Omniverse to design AI factories.
Mhm.
So are there any real life examples for that? And the accuracy of the AI model with a real life factory. What's the accuracy of that?
So I think the key thing to note is that one of the examples, so we are using this with Schneider Electric, right, and with our own factory. So I can share some examples of where this has been done. If you go to YouTube and look at BMW, there was an entire factory that was built inside Omniverse for BMW, right? So you can see how they designed it, how they simulated it, and then how they translated that simulation into real world. Of course, there is always going to be some gaps between simulate versus real world. You call that sim versus reality gap, and you got to close it continuously, right? But the objective here is that you are trying to figure everything out before you do it, so that you have lesser number of problems and faults, and you can get to the design cycles much faster, right? Versus physical way of doing it is, so one person is doing the layout, another person is doing the electrical, another person is doing the plumbing. All of them will put together in a spreadsheet, then somebody else look at it. Instead of that, people are working on multiple facets of an AI factory together. They're designing it to scale, they're simulating it, they're doing a number of scenarios, and then at the end of it, you're putting, actual construction, right? And no, so I think so. We've got 3 different platforms, one for HPC, one for simulation. The Omniverse, digital twin platform is a set of hardware and software that allows you to create those digital twins, OVX platform, and then there is platforms for training and inference. Yeah. I don't get your question. Why don't we take it after I'm done here? Yeah, let's just take it after I'm done. Yeah. All right. So let's get into the inference side. So as we talked about, is the age of edge AI is here, meaning each device that we are shipping now is intelligent. You see intelligence inside cameras, you see intelligence, inside many edge devices that allows them to run small models, and then they can take actions, right? In the past, that a lot of edge devices used to be quote unquote dumb, meaning they just are used to collect data and ship it to the cloud, and most of the intelligence then is generated there in the cloud, and then the actions are sent to people to go take it. That paradigm is about to change. The paradigm shift that you will have is you're going to have a distributed intelligence system. Of course, there is still the cloud, but intelligence is going to get distributed throughout the network, which then allows you to get to the autonomous operations and autonomous grid that we're talking about. So one example here, this what you see is a smart meter from a company called Utilidata. It uses NVIDIA's Jetson Edge devices. As you know, we provide a consistent platform across from the data center all the way to edge, meaning developers can build their solutions confidently across our entire stack, and we take up the complexity of making it work. This device allows you to understand and figure out the workloads that are running inside a facility, and then figures out when to store electricity, when to pull it from the grid, and also sends and analyzes a lot of data near to where the workload is, so you get the better understanding of the workload patterns, and then the optimization of the grid can be possible. So imagine if every factory, every home, every asset out there has this kind of a capability. It is then not only taking the data, creating intelligence, doing inference, and sending out those signals to the grid, right? And that can become an input for your digital twin of your grid, which allows you to optimize it at the system level. Hubble's Accelera is the first company to embed Karman, which is the AI platform for smart meters inside this. So meaning an entire AI platform allows you to, the developers that can now build applications for smart meters and deploy them at the edge. So far, I think we talked about how sort of the energy system is changing, how it is critical that we bring AI to the energy system. We talked about extreme co-engineering of data centers and AI factories to get the most performance per watt at the lowest possible cost. Then we spent time talking about how physical AI is impacting the energy system. We talked about the training, the simulation, and the inference computer. All three of them together are driving the transition from what we have, a system that is today with least amount of visibility, predictive analysis is hard to do, and then facility communication between the central grid and the edges is low, to the next step is central coordination, putting intelligence in every step of the place to get capture intelligence and do the coordination, and move to the future of autonomous grid. The future of the grid is autonomous. It is the largest robot on the planet. We're going to try to move away from a grid that is sort of manually managed to an intelligent grid and autonomous microgrids as a part of the entire system. Of course, we are a AI platform company, so that means we need a robust ecosystem of customers, partners, and solution providers that work with us, and we're enabling this through a vibrant ecosystem. We've got partnerships with utility companies. We just talked about one of the partnerships with EPRI, and also work with a lot of solution providers like Schneider Electric, ETAP, Aviva, Hitachi Energy, GE, all those kinds of companies that provide software today. We're working with them to bring AI to the grid. So, final thoughts. AI is enabling energy efficient computing, right? As energy is powering AI factories, AI tokens are making energy system more efficient. Complexity of the grid requires AI. It is humanly not possible to do this all manually or physically. So it definitely requires AI. Grid must be software defined. Very important point. So as we try to convert this physical infrastructure, it needs to be software defined, meaning more and more capabilities need to be pushed as we go towards autonomous capabilities. The future of the grid is an autonomous system, as we talked about. Technology to build the autonomous system is here, which we studied some of these components today, the simulations, the training, the edge inference, and the vibrant ecosystem, a large group of willing companies that are partnering, and open bodies that are helping with all of this. Open collaboration and partnerships are key. This is not a one company, one customer, one ISV problem. It is an entire ecosystem's problem and opportunity both. So that means vibrant ecosystem is absolutely essential for this to be successful. How How did you contribute to the resiliency and sustainability of the grid is going to be the legacy all of us will leave. Each one of you either work for an energy company, maybe you have strong interest in this area. I urge you to start looking at applying AI to everything you do in this industry, whether you be in oil and gas, whether you be in energy utilities. Think of AI as a force multiplier. Think of AI as something that is going to help you be more efficient, more proactive with everything you do. And I'm confident that the time for applying AI and high-end technologies to the grid is now, because the world needs this more so than ever before due to all the reindustrialization, build out of AI infrastructure, robotics, electrification, growth in population and human standards and raising global standards all around the world. It's not acceptable for people not to have electricity when they need it, the way they need it, and how they need it. And extreme co-design, engineering, bringing AI to the energy grid is essential to solve that problem and making it successful. Thank you for your attention today. On AI factories? Yeah, I have. I can share that with you. So if I sort of go back, let's show the. So this is the unit economics for LLM inference. From 2004 to 2025, you can see the orders of magnitude of power consumption. Look at the amount of power that that was required for a Kepler to what it's required for black hole ultra, right? So all of that is achieved through extreme co-engineering.
What I meant to say, for example, if I take a solution like utility data,
Yeah.
and somebody deploys it,
Yeah.
how does that unit economics work with what people today have with municipalities?
That's a good question. I think so for utility data we work with them closely. We can get you that information, but I don't have that offhand. Yeah.
Can you share some more information about your ecosystem partners
Yes.
and how you collaborate with
Yes.
them?
Yes.
And if there's any business opportunity that you see that you can put here with the AI?
Yes. I think we are exploring smart meters for India, is what I heard last, right? So there's significant amount of interest in putting smart meters, especially for large industrial facilities, right? And I think we made some connections between utility data and one of the customers. I don't know who it is exactly here, but there is significant amount of demand for smart meters here in India, right? So I can maybe let's touch base